All right, welcome back. So our previous video was focusing on oxidation states and how to determine them. So this video is going to be a little bit more specific, and what we're going to do is we're going to look at some reactions, and we're going to use those oxidation states to figure out if that reaction, which atoms are reduced and which are oxidized. So let's just we'll start off with very simple one. We're going to start off with hydrogen gas reacting with oxygen gas. Now, of course, the equation will need to be balanced, but the balancing of the equation does not make a difference in terms of the oxidation state. It's just a formality thing. So let me just go ahead and do that. And so the first thing I do is I look for any elements that are by themselves in their native state. So elements that, again, like hydrogen gas, oxygen gas, iron, copper, anything that's just sorted by itself typically has an oxidation state of 0 because they are in their native state. Now, as these two react, they'll form H2O, and the hydrogen, and this goes back to your periodic table, hydrogen is in group 1, which is +1, and I'm just going to go ahead and fill this in all the way through. So +3, plus -4, -3, 2, -1, and then 0. So hydrogen is +1 and the oxygen is -2. And these are just a few occasions where you can look at the periodic table for the oxidation state, and you don't have to back calculate like we did in our previous examples. So the hydrogen goes from 0 to +1, and the oxygen goes from 0 to -2. So based off what we said earlier, we talked about the fact that reduction is a gain of electrons, atoms would become more negative, and then oxidation is a loss of electrons becomes more. So looking at this, hydrogen is more positive, so it's oxidized, and that means that the oxygen itself is reduced. You cannot have a reduction without oxidation, and you cannot have oxidation without reduction. You have to have one. So once you figure out one, you know the other one pretty quickly. All right. So let's look at another molecule. So let's say we have NaCl. NaCl will break down to form sodium plus chlorine gas. And so again, we are going to look at the oxidation state for each of the elements. So find the ones that are by themselves. All right, that's sodium on the right and Cl2, which is on the right, and they're both 0. And then you go back to the reactant and say, well, okay, well, sodium is in group 1A, it's +1, and Cl is in group 7A, so that's -1. So the sodium goes from +1 to 0, and the chlorine goes from -1 to 0. All right, so in this particular example, the sodium is actually getting smaller. It's getting lesser, so therefore it's being reduced, and that means that the chlorine is oxidized. All right, one of the few times where you're going to see chlorine be oxidized. Chlorine is typically a good oxidizer, but that comes like later on. That's a more advanced topic, not something we're going to work with today. So all right, so let's take another one. So let's take a single replacement reaction. Take silver nitrate reacting with copper. It's going to form copper nitrate, and I'm not saying the charge yet because I wanted to figure out the charge. All right, plus silver. So elements that are by themselves can be 0. So copper is 0, and the silver is also 0. They're by themselves. Now, based off the periodic table, we're dealing with transition metals. Copper can either be +1 or +2. Silver is only +1. All right, so silver is the easy one here. It's the copper that we got to figure out through the back calculation process. So silver is +1. Now the nitrate doesn't matter. Nitrate, we call it a spectrate ion, so it doesn't make a difference. What does make a difference is the fact that the copper has 2 nitrates, and each nitrate's -1, so that's -2. That means the copper is a +2 charge for this example. So the copper goes from 0 to +2, and then silver goes from +1 to 0. All right, now it's clear that the copper is gaining positive charge, so it's going to be the one that we classify as oxidized, and that means that the silver is reduced. All right, so these are three fairly common, easy examples that we look at, and these are sort of basically what you see throughout the different types of reactions. But there are other more complex reactions where you can figure out, and I'll show you one here. So this is ammonium dichromate, and ammonium dichromate breaks down to form Cr2O3 plus N2 plus H2O. All right, and so looking at this, you're like, oh man, there is a lot here. All right, but there's a couple things that you can kind of narrow down fairly quickly. The first one is that I see a nitrogen that's by itself on the right. So I know that something's going on with the nitrogen because on the left side it's a part of a compound. And so anything that's part of a compound is going to have a charge. When it's by itself, it's going to be 0. So that's the first thing I noticed there. Now, the second thing I noticed is that this chromium has 7 oxygens, and then on the right hand side it's reduced down to 3 oxygens. So something's happening here. So we're going to look at this chromium. Now the oxygen staying the same. There's nothing there that looks like it needs to be addressed. Same thing for hydrogen. Now you say, well, what would it look like if it did have to be addressed? So it would be O2 or H2. So if you saw O2 or H2 in their gas form, then yes, that would be something that you would want to pay attention to. But that's not something that we see here, so we're not going to worry about it. What we are going to be concerned with are the chromium atoms and the nitrogen atoms. So now on the left side, the nitrogen is -3. You say, well, how do you know that? Look at the periodic table. Nitrogen is in group 5A, which is -3. All right. Chromium, however, is a little bit more involved. So this is dichromate. So what I'm going to do is I'm going to rewrite this down below. And I'm going to rewrite it in a way that just makes it a little bit easier, because that ammonium to the right, it's not terrible, but it's easier because you can back calculate this a little bit nicer. So this is -2. It's the charge of the dichromate ion is -2. You can figure that out because the ammonium is 2 and +1, so that's +2, and -2 cancels +2. All right, so the oxygen is -2, and that's typical. All right, 7 times -2 is -14, and that means that you have 12 minus 14 equals -2. So the difference is now the chromium there are 2 of those, so 12 divided by 2 gives me +6. So the chromium is +6 on the left. Now let's look at the chromium on the right, just see what it looks like it's doing here. So this molecule is neutral, so you set it equals 0. The charge on the oxygen is -2, that's -6, and 6 minus 6 equals 0. Now there are 2 chromiums again. 6 divided by 2 gives me 3. All right, so that means the chromium is +3 here. So the chromium changes from +6 to +3. The nitrogen changes from -3 to 0. So the chromium itself is reducing in charge. So it's reducing. It's reduced. All right. So that's what it is for the chromium. Remember. And then the nitrogen is oxidized because it's going up in charge. It's increasing in positivity. So these are our 4 examples. All right. The 4 examples. We start off with a very basic one. we do a little bit more involved, but not that much, because what we're doing is we're focusing on these native elements, and then we do a single replacement reaction. And now we've done a little bit more challenging one, which this one is a decomposition reaction. So what I want you to see here is that in these 4 examples, you've seen all 3. You have solved single replacement, synthesis, and decomposition reactions, and you can see how they're all relating back to this topic of redox reactions and oxidation states. So, all right, thanks for watching. That's the conclusion to this video. Thanks.